All right. So, good afternoon, everyone, and welcome to this session about repository mining with Clojure. Today, I want to give you a different perspective on your code base. And it's a perspective that will help you identify code that's hard to maintain, code at risk for defects, and code that becomes a team productivity bottleneck. And to do that, we need to go beyond code. So let's start by considering what we programmers actually do. Because we don't write code. Of course, we do that as well, otherwise we wouldn't have a conference here. But that's not where we spend the majority of our time. If you look at the research, you will see that most of our time is spent making modifications to existing code. And the majority of that time, in turn, is spent trying to understand what the code does in the first place. So if we want to optimize any aspect of software development, we should optimize for ease of change. And I think that's in line with Lehman's laws of software evolution. And these laws, they are more like a set of observations. And like all good things, they go all the way back to the 70s. And I like to present two of those laws to you here. And the first law is the law of continuing change, which says that a system has to continuously evolve, or it will become progressively less useful over time. And this is in contrast with the second law I'd like to present to you, the law of increasing complexity. And this law says that as a system evolves, its complexity will increase unless we actively try to reduce it. What I like about these two laws is that there is some tension between them. On the one hand, our code has to evolve in order to stay useful, but when it evolves, it becomes more complicated. So we have to fight that somehow. This is a hard problem. Before I go into that, I have a confession to make. I'm a .NET consultant. And what that means is that I spend most of my time working on systems like this. We have multiple subsystems distributed across multiple tiers, and that alone makes it pretty hard to get a holistic picture. Of course, these systems are also developed in multiple languages, which makes it even harder to reason about it. And if that wasn't enough, most projects today are developed by multiple programmers organized into multiple teams. And that leaves everyone with their own view of how the system looks. Now, this isn't just about technical complexity, because systems that look like that tend to come with an organization like this. So, given this mixture of technical and organizational social complexity, how can we find the code that really matters? Well, within the software industry, we have things like complexity metrics, right? So we have a bunch of them. We have things like McCabe's cyclomatic complexity. We have Halstead's volume measures. We have different measures for cohesion, and so on. There are a lot of them. What all of them have in common is that we take a tool, throw it at our code base, and out comes a list of every module with a nice complexity number. So why don't we use that more often to find the code that's hard to maintain? Well, I don't know, but I know why I don't use complexity metrics. And the reason I don't use complexity metrics is because complexity metrics are pretty bad at predicting complexity. It's perhaps a bold statement, so allow me to support it a little bit. If you look at the research, and there is some research that supports this, as soon as you start to control for the number of lines of code, more elaborate metrics don't add any further predictive value. The number of lines of code, that's a really rough metric. Is that the best we can do? But there's a second reason as well. Even if complexity metrics would magically work, they won't do the trick alone. Because complexity has this property. Complexity alone is never a problem. If we have some complicated code over here, and that code been stable for 5 years, it works wonderfully in production, and we never need to touch it, well, we probably all have much more urgent matters to attend to. So what I'm saying is that the code, how it looks today, is important. But it's even more important to understand how the code got that way in the first place. We have to understand the evolution of our code base, because if we understand the history of our code, we're able to project a trajectory into the future that helps us identify precisely that code that really matters. And so we would need somehow to get that evolutionary data. And the good news are, it's data that you all already have. We're just not used to think about it that way. I'm talking about our version control systems. Our version control systems, basically, they record every change we make to the software. And they also record social information, since we know which programmer that did the change. So what I suggest is that we take an evolutionary perspective on our code base. Here's how that may look. It may look like an alien, doesn't it? But it's not. This is 400,000 lines of code. And we're going to return to this visualization in just a minute. But please allow me to explain what you see there. In this visualization, each module, each class, is visualized as a circle. And those circles have two dimensions. First, size is used to represent complexity. So the larger the circle, the more complicated the code beneath it. But I also said that complexity alone wasn't good enough. So we add a second dimension too. And this is data mined from our version control system. That's the code change frequency in this case. And that allows us to spot an overlap between complicated code that we also have to work with often. And that's what we call a hotspot. So let's return to this visualization. This is an interactive map, so you can zoom around to the level of detail you're interested in. But even here, on the highest level view, we're able to detect a number of hotspots. Now, remember, hotspots are complicated code that we have to work with often. What kind of code is that? What will we find if we look into a hotspot? To answer that, I decided to mine a second set of metrics. I decided to mine our bug tracking system. And the reason I did that is because in most systems, bugs tend to be unevenly distributed. Some modules are just more defect dense than others. And when I correlated that to the hotspots, I found out that the hotspots identified 7 out of the 8 most defect dense parts. Even more interestingly, the hotspots only made up 4% of the code, yet that code was responsible for 72% of all defects. Or if we turn it around, in this particular system, if we improve just 4% of the code, we get rid of the majority of all defects. And a hotspot analysis points you to precisely those parts of the code base that really matter. And I'm going to show you a bunch of other analyses that you can do with version control data. But before we go there, let's discuss the tool I used to mine those metrics. When I started out with these techniques, like 4 or 5 years ago, I used a combination of shell scripts and Python code. And that worked pretty well for a long time. But then 2 years ago, I started to write about these techniques, and that's what eventually became Your Code as a Crime Scene. But I wanted to do something more. I wanted to give each of my readers the possibility to try these techniques out on their own code base. And there was really no responsible way I could take my unholy mess of shell scripts and Python and put that in the hands of someone else. So I decided to rewrite the whole thing from scratch. And I decided to do it in Clojure. Now, why Clojure? Well, Clojure is an excellent choice for data analysis. But I didn't know that 2 years ago. I was just lucky, really. The reason I chose Clojure was much simpler. It wasn't a technical choice at all. I just wanted to learn the language, and I wanted to learn it because it looked fun. And fun is a much underestimated driver of design. In fact, I would say fun is a much underestimated motivator in our industry. Fun is almost a guarantee that things get done. So that's why I choose Clojure. And the tool that I developed is called CodeMaat, and it's available on GitHub. You have the link over there, and you will get it once more at the end. It's an open source tool licensed under GPL. And CodeMaat is built around an architectural pattern called pipes and filters that I think works pretty well in a functional style. So CodeMaat is a command line tool, and it operates on version control logs. So we take those logs, throw them to a parser that converts the data to an internal data format that gets passed on to an aggregation step. Now, aggregation, that's things like, say you have a bunch of commits during a single day, and you want to take all those commits and consider them as one logical commit. That's one example of aggregation. So it's an optional step. And the result of that goes into an analysis stage where the actual calculations happen. And CodeMaat today supports, I think, 16 or 17 different analyses. And the result from that flows into the output module, and that's a really simple piece of code. We either just dump the thing to standard out so we can pipe it to another program or print it to a file. As I developed CodeMaat, I discovered a bunch of interesting libraries, and I think they are applicable way beyond this current application. So I would like to share what I found with you. And I would like to start by talking about parsing. So CodeMaat supports some of the popular version control systems. And those version control systems, they contain virtually the same information, but of course in radically different formats. It would be way too simple otherwise. So we basically had to write a parser for each version control system. And I sat down and looked at some different parser frameworks, but I pretty soon settled on Instaparse. And the reason for that is because I find Instaparse really, really simple. And Instaparse has as a design goal to make context-free grammars as simple as regular expressions. Now, if you've been doing regular expressions, you know that's pretty much a relative statement. But Instaparse really succeeds. And I want to give you a brief view of what it looks like. So we have one commit entry here from Git, from Clojure actually. And if we want to parse this with Instaparse, the first thing we have to do is to define a grammar. Here's what the grammar looks like for Git. So with Instaparse, we're pretty free with the format we choose. But what we did was basically that we introduced one rule for each element in the input that we are interested in. And once we have defined that grammar that describes the input, we just need to pass it to Instaparse parser function. And that's a function that generates another function, and that's our actual parser. So let me demonstrate that. We have our Git log here, and we have gotten this, we have defined a grammar, and we have gotten a function back that is able to parse this kind of input. So when we invoke it, we get Clojure data structures back. And in this case, the data is on hiccup format. But Instaparse also supports nlive. And I actually think that nlive would be a better fit for this particular application. So I'm going to look into that. So Instaparse was really easy to get started with, and it's something I definitely recommend if you're going to write a parser. And Instaparse also has a second design goal. It's supposed to be fast. And it looked pretty good at first. But then I tried to run the tool on projects with richer history, some of them going like 10, 15 years back in time. And suddenly, my program literally ground to a halt. It became slower than a Windows 95 reboot. I think that says something. So I was a bit surprised, and this was the first time that Clojure gave me a really hard time. I found it really hard to build a mental model of the performance due to the mix of laziness and non-laziness. So I pretty much gave up on that and threw a profiler at the code. And it turned out that the bottleneck was in the parsing stage. So again, Instaparse was supposed to be fast, and it turned out it is. It is really fast. But it's also quite memory hungry. It's a classic trade-off, isn't it? So Instaparse, in order to be able to backtrack, it needs to maintain a list of intermediate results, and that grows pretty fast. So once we realized that, the change was pretty simple. Instead of parsing the whole log in one sweep, we changed it to read lazily from the log file, line by line, and as soon as we had one complete entry, we threw that to Instaparse. And then we get the next entry, read it out, and parsed that in isolation, and so on. And once we did this tokenization, the performance problem went away. So that was a really simple change, and it's something I recommend. If you're using Instaparse on large input, please make sure to chunk it up. Your garbage collector is going to thank you. So that was a bit about Instaparse. I'm going to talk about some other libraries soon, but let's first discuss a second analysis. And I'd like to introduce it with one of the best quotes I know about software development. Code doesn't lie. If we want to understand how something really, really, really works, we have to look into the code. The truth is there, and it's described in very precise technical details. So, code doesn't lie, but it doesn't tell the whole truth either. And if we limit ourselves to what's visible in the code, we miss a lot of valuable information. And I want to show you one example on that. This is an analysis called Temporal Coupling, and that's something that you cannot measure from code alone. Temporal Coupling works like this. This is a simple system here. We just have 3 different modules. And in the first commit that we do, we change the fuel injector and the diagnostics module together. In the second commit, we're changing something else. In the third commit, we're back to changing the fuel injector and diagnostics module together again. Now, if this is a trend that continues, there has to be some kind of relationship between the fuel injector and diagnostics module, because they are changing together. What kind of relationship could that be? What you will find most of the time is this. You have some code over here, some other code here. This code uses that code, so every time you change this API, you have to change the client as well. And this is just our plain old physical coupling. And that's indeed something you can measure from code. But remember, temporal coupling wasn't measured from code. It was measured from the evolution of the code, from the version control history. So that means you will sometimes find cases like this. You have some code over here, some other code here, and there's no dependency at all between them, yet they keep changing together over time. How can that be? Is that some kind of spooky quantum physics process? Usually not. What I tend to find when I look into those cases is a good, dear old friend. Copy-paste. So you have some code over here, you copy-paste it here and here, and now each time you modify the original, you have to remember to modify the copies as well. So temporal coupling is indeed a great tool to detect software clones. But temporal coupling isn't always bad. Sometimes you actually want temporal coupling. And I'd like to show you an example from Clojure itself. If we turn back time almost 10 years to 2006, Clojure at that time was developed in parallel on both the CLR and the JVM. At least that's what's evident from the version control logs. So you will see that there was a C# class called persistent list map. And there was a Java equivalent called persistent list map.java. And if we measure temporal coupling in those early days of Clojure, you will find that those 2 classes change together 83% of the time. And in this case, that's actually the kind of coupling you want. So if that's the coupling you expect, why not use that to our advantage? So what I'm working on right now is to design commit hooks for Git that will check this kind of expected temporal coupling. So say you're working on these polyglot code bases, and you make a change here over here in .NET land, and then you want to commit that, you get a warning that says, hey, normally when you do these kind of changes, you also make a change over here. Do you want to continue? I think that could be genuinely useful. But there's more we can do with temporal coupling. Temporal coupling isn't limited to individual modules or classes. We can analyze complete software architectures with it. And I'd like to show you a brief example. I want to show you a microservice architecture. And the reason I choose microservices is because right now, microservices are all the rage. And that just means that tomorrow's legacy systems are going to be microservices. So this is what microservices look like in PowerPoint. In reality, they tend to look a little bit more like this. So we are programmers. We don't like to repeat ourselves. So why don't we extract a set of shared utilities? Perhaps we even encapsulate the communication. And of course, we follow the recommendation of providing a service template shared between all our microservices. And of course, we want to make it as easy as possible to consume our services. So let's introduce a bunch of client libraries here. Now, in microservices, low coupling is king. As soon as we start to couple different services to each other, we lose most of the advantages of a microservice architecture, and we're left with an excess mess of complexity. So what I recommend, and that's something that's applicable to all kinds of architectures, is that we try to do a temporal coupling analysis on this level and spot temporal couples that violate our architectural principles. So we want to investigate things like this, where services are coupled to a shared library. Or even worse, temporal coupling where multiple services change together. So to do those kind of things, you need the aggregation step I talked about. I won't go into the details now, but if you're interested in that, just talk to me afterwards, and I'll be happy to show you. I want to talk a little bit about Clojure again. CodeMaat builds quite heavily on a library called Incanter. So let me see, how many of you are familiar with Incanter? Oh, cool, something like 10–15% of you. So Incanter is a set of libraries for doing statistical computing. And to do something interesting with Incanter, you have to get your data into a dataset. A dataset is basically just like a table. You have a bunch of columns, and then you have rows for each entry in your data. And the cool thing with Incanter is that you get a lot of things out of the box. And I want to show you one example. I want to show you how to do a code churn analysis. Is anyone familiar with code churn? Some of you, great. So code churn basically refers to the amount of change in your system. So if you add 5 lines of code, you have a positive churn of 5. If you remove 10 lines of code, you have a negative churn of 10. And the interesting thing with code churn is never the absolute numbers. The interesting thing with code churn is the trend over time. And you see an example of that here from one particular system. And see those large red lines? Those are the raw churn values over time. Now, we have a second dimension there as well. We have a rolling average. And a rolling average, it's a great way to remove fluctuations in your data in order to be able to spot a possible long-term trend. So a rolling average is like a sliding window. Imagine you put a sliding window on your data, calculate an average, move it one step, calculate a new average, move it one step, and so on. So I said that the interesting thing is the trend. And that's because code churn is one of the best predictors of post-release defects. The higher the churn, the more post-release defects. So in this case, you see that the churn here over the past months has been increasing. And if this is a project that is approaching a deadline or a release here, that's a clear warning sign. That sign means that this code base isn't ready for release. There's a lot of work left before you have a stable code base at that point in time. So I want to show you how these kind of charts are generated with Incanter. If you run a code churn analysis with CodeMaat, you get a CSV file as output, where you can see the code churn, the raw churn values, organized by day. Remember with Incanter, if we want to do something interesting with Incanter, we have to get the data into a dataset. And that's pretty simple, since Incanter comes with a read dataset function. So we just point it to our CSV file, and we see here a pre-printed Incanter dataset. And you see it has the same columns as our input data. So now, since we're interested in a trend over time, a time series, we should really look into the Incanter.Zoo library. And to do something with Zoo, we need to have a Zoo value. A Zoo value is basically just another Incanter dataset, but with one special column, a special index column containing datetime objects that specify our time series. So we can create the Zoo object, a Zoo value, by calling the Zoo function, passing our dataset, and specifying the column that contains the time series. And that's basically it. So we get a Zoo value back. You see the index column here with the datetime objects. Now, the next thing we wanted to do was calculate the rolling average. Remember, our sliding window. And that's pretty simple with Incanter. The only thing we have to do here is we use some Incanter magic to extract the added column, because that's the best predictor when it comes to code churn. And then we pass that to Zoo's roll mean function. And we also specify a width or a sliding window. And my general recommendation is to choose something that means something in your particular context. So let's say you have working iterations of 2 weeks. Choose a sliding window of 2 weeks. So the values we get back for roll mean, we feed them, create a new data set, and merge that with the original data set. So we get a new data set back. And this new data set contains a rolling added column. On a large system, you have a lot of data. So we need some kind of algorithm to detect patterns in that data. And my suggestion is that we choose the best known pattern detector in the universe, our visual brain. So the only thing we have to do is to visualize that data, and that's quite straightforward with Incanter, because Incanter includes a charts library. And in Incanter charts, you will find most of the common charts. In this case, we're interested in the time series plot. So we choose that chart, and we pass it our dates, but converted to milliseconds since 1970, because that's what the underlying library wants. And then we pass the raw churn values for that time series, and we also specify a bunch of properties here that will be included on our chart. And once we run this function with the data we had earlier, we get something that we can view, a chart like this. Now, this is a different data set than the one I showed you earlier. This is from Microsoft's Roslyn project. And Roslyn is like Microsoft's open source flagship product. It's a compiler platform for .NET. And this code churn was calculated just as Roslyn hit its first release. And you see here on the rolling average, you see that there was a peak of activity at the beginning of the year, and then it declined, and the code base kind of stabilized over the last months here. And I think in general, if you work in this traditional model, I think that's just the kind of churn you want to see in your own projects. A code base becomes more and more stable as it approaches a release. All right. Do you remember that I told you that I use to work on systems that look like this, that usually come with an organization like that. That means I sometimes have to take a step back and remind myself why programming used to be fun. And the way I've been doing that is by hacking around in processing. Processing is a language and environment for creative coding. And it's pretty much a library built on top of Java. It tends to be a bit more procedural than Java. And you see some examples on processing sketches here. And what I find so liberating about programming processing is that I try to break every best practice there is. I try to break every known design principle. I use global variables. I mutate state. I nest conditional logic, and I never write a single test. And it's so fun. So when I started to work with these kind of techniques, I used processing to do the visualizations as well, because I already knew the language. So here's an example of that. This is a tree map showing the changed frequencies mined from version control data in one particular code base. But it soon turned out that, yeah, it was fun and liberating to start with, but it wasn't as fun once I had to maintain those programs. So that's why I'm happy to learn that Clojure has an alternative, Quil. How many of you have worked with Quil? Oh, like 20% of you, great. So Quil is a wrapper around processing. And I really just want to show the programming model here. Quil is even more fun than processing. A Quil uses the basic concept called a sketch. So we use a macro def sketch to define our sketch. That's just as in processing. We also have to specify a setup function. And setup is something that Quil would call for us once at startup to create the initial state. That's just as in processing as well. And then we have to specify a draw function. And draw will be called repeatedly to do something interesting on screen. So far, that's exactly the programming model of processing. But Quil takes it one step further. Quil allows us to specify a set of middlewares. In this case, I'm using something called the fun mode. And what the fun mode does is that it removes the need for those shared global variables, because fun mode allows me to program using a functional style. So now, with fun mode, setup will return the initial state, and that will be passed into draw that returns the next state, and so on. And if you have things like mouse event handlers, you're doing interactive visualizations, those event handlers will be passed the old state and return the new state. So with the middleware and Quil, that's a huge improvement over processing. Of course, you still have a bunch of side effects, and I don't want to go into the details, but basically, every time you want to do something interesting on screen, it's going to be a side effect. So you want to specify a background color or draw a text or draw a line, side effects. But at least we can program in a functional style in Quil. So I used Quil to solve the following problem. I already talked about predictors of defects. It turns out that one of the very best predictors is the number of programmers behind a piece of code. The more programmers behind a piece of code, the more quality issues within that code. And I started to think, well, again, that's data that we actually can deduce from our version control system. So what if we can find those modules in our system that suffer from excess parallel development? And again, it will be a lot of data, so I needed a way to visualize it, and I choose to use Quil for that. And I used a visualization technique called fractal figures. And fractal figures is a technique from this academic paper down here. And fractal figures works like this. You consider each module a box, and each programmer gets assigned a color. And the more that programmer has contributed, the larger the area of the box. So here is an example from Clojure. And if we're after access parallel development, we have two modules that really stick out here. One of them is the compilation module, and the second one is a Java class called numbers. And I think this is the great thing with Fractal figures, because even though those two modules have approximately the same amount of contributors, the patterns look radically different. You see the pattern to the right. I would say that's quite unlikely to be a problem, because we see that dark blue developer has written virtually all the code, and we just have small contributions from other programmers. So probably we have quite a consistent style and programming model there. Now, Clojure and open source is a bit special due to the review process in Clojure, but if this was a closed source project, I would be worried about the pattern to the left. Because you have a lot of different programmers that all wrote parts of a larger module. So it's quite likely that we will find inconsistencies and duplications within that code. So if you find something like that in your code base, you have to look into it, investigate it, and understand why. And I promise you, what you will find most of the time is that code changes for a reason. The reason code attracts many programmers is because it has many reasons to do so. It probably has way too many responsibilities. So I think that Fractal figures are useful even without knowing the programmer behind each color. But of course, we can add that information as well and get a second use for it. Now we can use it as a communication aid. So for example, say I want to know about the evaluation module over here. We see that it's the light blue developer, so that's Stuart Holloway. He's the one who knows how that works. And if I want to know something about Clojure in general, it seems like the dark blue developer has contributed a lot. That's a guy named Rich Hickey. So he probably knows a thing or two about Clojure. So my goal in this presentation was to show you some examples of the wealth of information that's stored in our version control systems and how we can mine and analyze it with Clojure. And this presentation has really just scratched the surface of what's possible. And you see a bunch of different examples here. Here's an attempt to visualize the communication paths between programmers. We have code age diagrams, so you can detect the relative stability of packages. And we have knowledge diagrams and a lot of other stuff. If you want to dive deeper into this field, I put together a set of blogs here that introduces some of the topics. And of course, there's also the book. And most importantly, you have the source code for Maat here. And I would be both happy and honored to accept pull requests. Now, before I leave you, I just want to take the time and say thanks a lot for listening to me, and may the code be with you. Thanks.